Thanks, thanks, Bernhard. I'm delighted to be here. That seems a little loud. Is that too loud? I kind of shout if I get sort of excited when I lecture. I also sometimes go kind of fast. Bernhard told me I've actually lost 15 minutes already, so I don't know what I'm going to skip yet, so it'll be a little bit dynamic. But the other thing I like to do is first get a sense of the audience, because I know all of you are here interested in machine learning, and I'm going to talk about a computer vision problem called optical flow. And the secret that I'm going to let you in on right off the bat is there's been almost no work on machine learning and optical flow. Now that's not entirely true, and I'll point out a few little things. And we'll talk about why that may be the case. But that means that there's a huge opportunity here to do something new and to take everything you've learned in the last 2 weeks and apply it to this wonderful problem of optical flow estimation. So before I get started, how many of you know what optical flow is? Okay. How many of those who know have used an optical flow algorithm for some purpose? Okay. And how many of you have actually implemented an optical flow algorithm? Okay, so there's like 2 people who will be bored in the beginning. So what I'm going to do is take you through, introduce you to the problem, what it is, why people may care about it, and then give you some sort of the introductory things. This is not optical flow advanced level. This is, I'll do the introduction and take you through the formulation that I consider the classical one. If you pick up a paper on optical flow to read it, you'll want to understand this classical formulation. That doesn't mean it's the right formulation. This is very important, particularly when you start thinking about maybe applying machine learning algorithms. Maybe the classical formulation is not the right formulation, but it's important to understand it. And then I will, for those of you who get so excited about this, there'll be code, and you can take it away and play with it and improve upon it and have a foundation to start with, and it's reasonably decent code. And then give you an idea of where machine learning might play a role. So the term optical flow goes back at least to the work of the psychologist Gibson in his work on ecological perception. And the idea is that as I move through the world, or a bird or any kind of animal moves through the environment, there's a changing pattern that spreads across what Gibson called the optic array. But in a camera, it would be the image plane of a camera. So you have this constantly changing pattern as you move through the world. And this pattern induces what Gibson called a flow. And this flow is the motion of the luminance pattern on the image sensor. And the reason Gibson thought that was important is it gave, in his mind, direct access to properties of the world that were important for an organism to survive. So for example, if I'm an organism that happens to be an airplane and I want to land on this runway, the pattern of flow, shown here by these vectors, gives a sense of what I'm approaching, that I'm approaching this location here, and I'm not about to crash into the ground. And this might be useful if you're a rabbit and you want to hide in a hole. As you approach a hole, there's a particular distinct pattern of optical flow that you might recognize and be able to exploit. If a lion's jumping out to eat you, that will also present a distinct pattern of optical flow that's probably worth recognizing. So this notion is grounded in this, what Gibson called ecological optics, and but there's also a mathematical definition of it. So let's consider a very simple world in which we have a camera. This is my camera. And there's a focal length of this camera and an image plane. And the camera can, there's only 6 things the camera can do. It can translate in space, X, Y, and Z, and it can rotate in X, Y, and Z. So there's 6 degrees of freedom here. And imagine I have a point out in the world, capital P, and it projects to some point, little p, in the image plane. As the camera moves, the projection of this point onto the image plane moves, and it induces a 2-dimensional vector, which describes the motion of that 3-dimensional point in the world, and that is something that we call the motion field. Now, there's a couple of things to notice here. The first thing is the 3-dimensional motion of this pixel, 1 dimension is lost in the projection onto the image plane. So we don't get back the 3-dimensional structure of the world. We get back something related to the 3-dimensional structure of the world, but missing a little piece of information. Now, This is what's called the motion field. It's related to the three-dimensional structure of the scene and how it is actually moving. Optical flow is actually a slightly different problem, or has a different formulation or definition. In fact, it is the 2D velocity field describing the apparent motion in the image. Now this is going to be, these two things are going to be different. So here's a first thought experiment. Imagine a matte ball. So this is a Lambertian ball. It reflects light in all directions. So it's really diffuse, okay? And imagine it's rotating about the vertical axis in 3D. So it's spinning around. What does the motion field look like? So someone's pointing, so it's kind of like a horizontal motion, right? So what does the optical flow look like? It's constant, 0, no optical flow. You don't see anything in this case. So now imagine this case. I've got a stationary ball, and I'm moving the light source around it. What is the motion field? I see some motion. The motion field, I see a lot of hands waving. What else? There's some vague sense the motion field looks like this. Remember, the motion is the three-dimensional motion of points in the world. The ball is stationary. It's constant. That's right. So the motion field here is 0. And what's the optical flow look like? Those of you who were waving your hands before should now wave them. So these are two cases where the motion field and the optical flow field differ. And that tells us something right away. It tells us that if we compute the optical flow, we may not be able to immediately get back to the three-dimensional structure of the world and what's actually happening in it. Maybe. So that's just important to keep in mind as we go forward. So let me define a little bit more precisely what I mean by optical flow, and we'll define some terms. So here's two frames. And this, oh yeah. What, too close? Okay, is that better? All right, thank you. Thank you for asking a question, putting up your hand. Even though it wasn't related to the talk, it's still good, and I like questions, so ask more of those. So here are two frames in a video sequence, and for the most of the rest of this talk, we'll talk about only two frames, which may be kind of a crazy thing to do, but that's what we're going to do. So here's two frames. And the image intensity function, I, is a function of the spatial position of the pixels, x, y, and the time t, okay? And I'll use boldface typically to represent a vector. So boldface x here is x, y. And then we think of this, we can think about how a point in here moves as a vector in 2D with a horizontal component, which is called traditionally u, and a vertical component called v. Don't ask me why this isn't h and v. It makes no sense, but that's how it is. And it's a function of x, y, and maybe also t, but we're going to ignore t here. And so this vector field, it's kind of hard to see vector field, so we're going to color code it in the following way. Small motions are going to be highly close to white or not very saturated. The larger the motion, the more saturated, and color is going to encode the direction. So this is an example of the optical flow between these two pairs of frames. So how every pixel moved. Remember, it's the apparent motion of the pixels. Any questions so far about the representation? Okay, so we're going to, just as a little aside, we're going to now forget everything we might know about physics. So that maybe, it's always a dangerous thing to start out a talk by saying, let's forget physics. We will come back at the end of the talk to think that maybe physics might play a role and be an interesting thing to think about, but we're going to do that. We're going to forget everything we know about materials and light and optics and all of that stuff, and we're just going to focus on images and these pixel values in images. And so that's going to be what we do today. Now, I want to point out that there's lots of applications of optical flow. Lots of people do structure from motion. They try to estimate how camera moves through the world. They try to estimate the 3D structure of the world. They try to estimate where there are motion boundaries in the scene. And there's lots and lots of recent applications, particularly in the graphics area, but video coding and compression uses optical flow to obviously figure out what's constant over time in a video and use that for compression. You can use it for pedestrian detection, video denoising, image resizing. You can analyze plant growth and the motion of ocean currents and meteorological information. People use optical flow all over the place. And one neat application is the one called the painterly effect. And this is why it's useful to put your code online if you're a PhD student, because these folks who made this movie, What Dreams May Come, downloaded my PhD code, and then every night they would shoot Robin Williams. Well, they would shoot Robin Williams moving around in a world, and then they'd take the footage, digitize it, compute optical flow on all the frames, and then they had an artist paint one of the frames with an impressionist painting. And then they took the optical flow field and used it to take the paint and move the paint around as though it were moving like the stuff in the world. So they had things like trees blowing in the wind and grass and water, and it all moved and looked like a very beautiful moving painting. It was supposed to be heaven. And anyway, they won an Academy Award for this, and I got nothing. But that's another reason to be careful about putting your code online from your PhD thesis. But whatever. Another movie that used optical flow heavily, you've probably seen, is The Matrix. For the bullet time sequences, they shot actors from many cameras, and then they computed the optical flow between the views of the cameras, and over time, and then they were able to interpolate any point in space and time fairly realistically. Matrix Reloaded, actually they also stole my code from my thesis, and they used it, but they applied it not to images, but to 3D faces. They just took the same code and applied it to models of faces, so they were able to morph faces and then reproduce new faces in poses that they hadn't seen before, facial expressions and so on. Anyway, so lots of applications. But how are you going to do it? So our goal is to compute this 2D motion of pixels from one frame to another in a video sequence. Now, there's a bunch of steps that we're going to step through. The first is we're going to make some assumptions about the problem. And it's important to examine your assumptions. And so we'll come back again and again to what assumptions we're making, try to make them explicit, try to make them clear, and figure out where the assumptions might be a problem. Now, once you've got some assumptions about the problem, we're going to formalize it. We're going to formalize a function that we can optimize. And it's, as this suggests, there's going to be local optima we have to deal with. Given a particular objective function, we're going to have to come up with some kind of optimization method. For optical flow, this turns out to be fairly specific to the flow problem. There's a bunch of features about it that you'll see that make it a little tricky. And then the unfortunate part that's often left out of many papers, the dirty secrets and the implementation details. This is where you get your hands dirty, and this is what separates the good algorithms from the bad algorithms often, is how they're implemented. And all these things work together. And then there's one other little piece, which is how do you evaluate? And this is really important, and we'll come back to all of these things. But let's start with our assumptions. The first and most famous assumption of optical flow is one that's called brightness constancy. And so the idea here is, here's two frames again in a video sequence. And the idea is if we look at a little patch, let's say look at this patch or this patch here, that there's a structure in the scene that's moving, but its appearance doesn't really change very much. Its 2D location changes, but the pattern stays roughly the same, and the same here. So we're going to make an assumption that the image at time x, position x, y, and at time t, looks like the image at the next time instant, t plus 1, but just so the pixels have been offset by this u and v. I've left out the x and y indices for the u and v. I'll be a little sloppy with indices. So if it's not clear, stick your hand up. So that's the fundamental assumption behind most optical flow algorithms. It turns out we're going to need another assumption, and it'll become clear in a moment why. But the other one is spatial smoothness. And here we're going to assume that neighboring pixels in an image are likely to belong to the same surface. And that seems kind of a reasonable assumption. Like, you know, these two pixels here probably belong to a surface. These two pixels probably belong to a surface. And so we're going to look at a pixel grid, and we're going to, for every pixel in the grid, we're going to look at the four nearest neighbors, and we're going to assume they belong to the same surface. And if they belong to the same surface, surfaces in the world tend to be kind of smooth. And if the surfaces are smooth, then the optical flow at those pixel locations is probably similar. Okay. That's just an assumption. And so I'm just going to write this assumption as, for a particular pixel P, the flow, say the horizontal flow U, should look like the horizontal flow at a neighboring pixel N in some neighborhood of P. another way to say this is we think the spatial derivative of the optical flow field is 0. So given those assumptions, we can begin to formalize an objective function we could optimize. So let's put the first one in. So we have a data term, we'll call it E sub d. It's a function of the flow vectors, horizontal and vertical component. And it's just going to be a sum over all the pixels in the image. And I'll assume that, I'm assuming these two things are the same, and I'm going to put a quadratic penalty function here that we want to minimize. Okay? So here's a new assumption I just made. I just stuck a 2 here, which implied something about the noise distribution I expect, and in particular that I assume it's Gaussian. Now, I'm going to define a spatial term, E sub s, which is a function of the flow field, and it's just going to be this pairwise Markov random field term I just described for you. Again, I'm going to put 2's here, which is going to assume that the flow field is smooth, that deviations from smooth are Gaussian, and first order smoothness is all that matters. I only care about first derivatives, and in fact, that I can approximate them, the derivatives with first differences. All of these are assumptions. All of them are actually not very good, but that it's important to write down what our assumptions are. Then, I'm going to put these two things together with a weighting term here, lambda. We're going to have to deal with that at some point. And now I have an energy function, E, which combines a data term and a spatial term and looks like this. That's the classical formulation of the optical flow objective function. So let's solve this, right? So now we come to the optimization part, but to solve it, it gets just slightly tricky. The problem is that this function and the derivative of this function is not linear in the flow field. The problem is the thing we want to solve for, this flow vectors at a pixel, u and v, they're stuck inside this function, this image function, and that makes it a little hard to optimize. So we'd like to actually get them out of there, and the easiest way to do that is to linearize this using a Taylor series approximation. So this is what's typically done. We take this term, the image, with the flow offsets. We do a first order Taylor series approximation. So we write the image xy at time t, and the partial derivative of the image in the x direction, the y direction, and the t direction. And these two terms cancel out. And so we're left with this equation where I've just replaced dx with u, dy with v, and we're assuming that dt, dt is small. And so we end up with the following equation, which is typically written in the following way. Ix is the partial derivative of the image in the x direction times the flow vector u, the partial derivative in the y direction times the flow vector v, plus the temporal derivative of the image. And we're assuming, again, that this equals 0. So this is called the optical flow constraint equation. We've made a bunch of new assumptions here. In particular, to do this first order Taylor series approximation, we assumed that the optical flow was small, and we could do this. We assumed that the image is a differentiable function, which it's this discrete thing, and so we're going to have to approximate those derivatives. And we also assumed that just the first order Taylor series was all that we needed. So a bunch more assumptions. So we're starting to pile assumptions on top of assumptions here. It's getting a little unwieldy. So let's look at this constraint at every pixel that we have. So it's a single equation with two unknowns, u and v, horizontal and vertical motion. So it's one equation with two unknowns, so that gives us a line. And it means that we don't actually know what the flow is along this line. We know it's constrained to lie along it. And this is why optical flow, you'll hear it described as an ill-posed problem. And it's this very reason. And you'll also hear something called the aperture problem. So I want you to look at this motion and tell me what is the motion of the line. Where is it? How's it moving? What direction? Point. Oh, up and to the right. Exactly. That's great. It actually could be moving in any of these directions. You don't really know. So I'm looking through an aperture here, a hole. That's one way to think about it. And that there's some line moving behind the hole. And the motion at this point is constrained to lie along this line, but I don't know in what direction it's moving. So the truth is, this is the true video. I just, in PowerPoint, I pushed this to the background so you can see what was actually happening. This was the actual motion, right? But you interpreted it as moving up and to the right. So it was actually completely horizontal. So this is the idea that at a single small region in the image, you might not have enough information to disambiguate what the optical flow is, and that what you're getting at a single point is a constraint that's ambiguous, and the motion could lie anywhere along this line. Any questions so far? I'm going a little fast because I want to get to some stuff. So this is the interpretation that you had and most humans have, and the reason that when I play this, you don't have that is you see these endpoints, and the endpoints are not ambiguous, or they're ambiguous in a different way. And the overall best solution for the line is horizontal motion. So I don't know, people have maybe heard of this aperture problem before and the optical flow constraint equation, but it's really useful to visualize what's going on. Here's an image sequence, 2 frames of a Pepsi can. And if we look in this little region, this red region here, every single pixel has one of these constraint lines. Remember, it takes into account the partial derivatives of the image intensity function in the x and y direction. And because there are many orientations to that intensity function in the image, we've got horizontal lines and vertical lines and lines at all kinds of orientations, we end up with constraint lines at all kinds of orientations also. And I'm just plotting all of the constraint lines in this little, probably not all of them, some fraction of the constraint lines in this little window. And you'll notice that they all intersect at a point, or kind of mostly sort of intersect at a point. This is the point that satisfies all of these constraints together. And so that's what we would like to find in any given region of the image, a unique estimate of the motion that satisfies a bunch of constraints like this. So there's a bunch of ways to do that. The first way, and the most famous one, comes from a paper from 1981 by Horn and Schunk. Horn and Schunk, often you hear, if you look at optical flow at all, you'll hear about these guys. And they wrote a paper called Determining Optical Flow. And they wrote down exactly this objective function I wrote down for you. Quadratic error term, quadratic spatial term, lambda term, weighting these 2 things. And then they did their best to optimize it. And so this is where the optimization becomes important. So remember, Horn and Schunk were working in 1981. Computers weren't that good in 1981. So they had to do a bunch of stuff to try and solve this problem. It was even hard to get image sequences into a computer in 1981. So it was pretty impressive. So they wrote down this objective function. And the way, and this is already linearized here. This is our Taylor series approximation, right? So they have this objective function. And they said, well, let's solve for that. Let's differentiate it with respect to the parameters u and v and set it equal to 0. That's just what you would do. Like, how do you solve this? Differentiate it, set it equal to 0, and then solve. And if you differentiate this thing and set it equal to 0, you get a system of equations that are linear in u and v. So they end up with a system of linear equations, and you can take these and you can, I'll just write them out as matrices here, just schematically. There's a data term, which is a diagonal matrix, and a spatial term, which is a banded diagonal matrix of some form. And then on the right-hand side, you have some product of the temporal derivative of the image and the spatial partial spatial derivatives of the image. So this is just a big system of linear equations. Easy to solve. You just write it this way. You've got your sparse, it's sparse also, and so you solve for that. But Horn and Schunk were working in 1981. So they said, well, we now have a pair of equations for each point in the image. It would be very costly to solve these equations simultaneously by one of the standard methods. So they implemented a really, really bad algorithm, really bad approximation. And this is where the implementation details matter. They knew what to do, they just couldn't do it. And consequently, in every comparison for the 30 years after that, they got slammed as having like the worst algorithm in history. Like here is a table from an early evaluation of optical flow results, and on this synthetic Yosemite Valley image sequence, and Horn and Schunck got the worst possible performance. They got more than 30 degrees of angular error. They were just like wrong all the time. So actually, for many years, people said optical flow, it just can't be solved. It's ill-posed. You formulate this objective function. You can't optimize it. The problem is just not even worth thinking about. And but it turns out what people weren't doing is just looking at all of the assumptions and the implementation details. So here are our assumptions, the big ones. Brightness is constant. Deviations from constancy are Gaussian. Motions are small, i.e. less than 1 pixel. Horn and Schunck assumed that also. First order Taylor is a good approximation. The image is differentiable. The flow field is smooth. Deviations from smooth are Gaussian. First order smoothness is all that matters. Flow derivatives are approximated by first differences. Well, some of these assumptions are not so good, but they're easy to fix. And so we actually, just today I got mail from the International Journal of Computer Vision saying that our paper on this topic just appeared this morning. So, and it's with a former student of mine, Ching Sun, and another former student of mine, Stefan Roth. And we decided to look at all of these assumptions and try to figure out which ones were really causing the problems, which ones mattered, and how could you fix them. And to do that, we systematically changed only one of them at a time, which is something people hadn't been doing before. So I'm going to go through a few of these and give you hopefully some insights. I have time, I think, into what matters and how people have dealt with them. So the first one, this linearization, remember, requires that this Taylor series approximation to be valid, which requires that the flow be less than a pixel. So that's no good, because real motions in real video sequences, in an action movie, something could move 100 pixels from one side of the image to another, or even 200 pixels in a widescreen movie. So the assumption of small motions just doesn't hold. Well, back already in 1992, and even earlier, probably Ted Adelson was thinking about how to formulate this nicely. And the idea was to build an image pyramid. So you start, so the image pyramid is just you convolve this with a Gaussian and you subsample and you repeat that. There's lots of variations on the theme, but that's the basic idea. So we have image 1, image 2, convert them into this spatial pyramid. And why is this important? Well, imagine I have a magnitude of my motion is 10 pixels here. At this, up here it'll only be 5 pixels, and here 2.5 pixels, and here 1.5 pixels. Now I'm pretty close for this assumption I was making of small motion is mostly valid. And so I can apply my optical flow equation here with my linearized brightness term and get a reasonable result. So that's what we do. I'm calling it W here, unfortunately. W is U. I just couldn't edit this for some reason. So this is the optical flow field U at a particular level in the pyramid. We estimate it by optimizing this thing, and I haven't, by solving this system of linear equations, et cetera. Then I take my image and I warp it by the optical flow, and I'm not going to tell you exactly how to do that. There's a bunch of ways to do that. And then I refine this, and then I project it to the next level. So I basically compute an approximation at the coarse scale, and then multiply it by a factor of 2 and increase its size, and I get an estimate for what's going on at the next level. And then I warp this by that estimate, refine it, and repeat. And this way I get incrementally estimate the large motions down here at the bottom. And this works pretty well. Most optical flow algorithms do something like this. And there's one neat little thing. It turns out there's a tiny little change you can make. Typically these are symmetric. So you subsample the image in the same amount in the vertical and horizontal direction. But with widescreen movies, you end up with, because they're widescreen, directors shoot them with a lot more horizontal motions and much bigger horizontal motions. So if you just subsample more in the horizontal direction, you can capture much wider motions. And people hadn't had that before, but it works really nicely. So Another thing that's important is if you're going to take something discretely sampled like an image, and compute derivatives of it, you have to do that in a nice way. I'm not going to tell you how to do it, but it turns out to be moderately important. But if you do all of that, okay, so you do this course-defined thing, you implement the optimization by solving a system of linear equations as opposed to Horn and Shunk's crummy method, and you implement your filters in a nice way, then Horn and Shunk isn't so bad. The basic formulation, the assumptions of brightness, constancy, and spatial smoothness with Gaussian noise actually produce an optical flow field here that isn't too bad. It has some properties. For example, it's over-smoothed, as we would expect, because this assumption of Gaussian noise on the spatial term applies that everything should be smooth. So at sharp discontinuities, we get, here's the ground truth. Here's what it should look like. And you see this, this is a shell here moving. And you see its motion is pretty sharp in the real world because it's two different surfaces. And Horn and Shunk tends to blur it. But it's not terrible. Yeah, sure.
You showed a comparison of different approaches.
Mm-hmm. Yeah.
The big table. Have they ever compared different techniques on image sequences at different frame rates? Because I reckon Horn and Shunk's assumptions, even though they're not exactly practical, but in those high frame rate cameras, they work pretty well.
Yes. So, indeed. I don't know that anyone's actually done a study with high frame rate cameras, but you're absolutely right. That makes many of the assumptions hold. The pyramid effectively does that for larger frame rates. The people are more interested in pushing the problem of really large motions, as we'll come to at the end, because this is what happens in natural movies that you get. So there's another way of thinking about this problem, which I didn't go into as this objective function I wrote down is just the negative logarithm of some probabilistic formulation where we're trying to model the probability of a flow field U and V conditioned on two images, I1 and IT, and it's proportional to a likelihood term, which is the probability of IT conditioned on the previous image and the optical flow, and a prior on the optical flow. And so this was our data term, and this was our spatial term, and there's a bunch of formulations that look at this in a more probabilistic way, and I'm not going to go into those today. We're going to stick with this good old-fashioned energy function formulation for now. So we thought about these problems, and fixing those makes a big difference. There's these other big problems. That brightness is constant and that the flow field is smooth. Now, probably bad assumptions. So let's look at those. The problem is, how do we know how to do that? To do it, to understand what the truth is, like does brightness constancy hold? Are the spatial derivatives of optical flow actually Gaussian? We would need some ground truth optical flow. So what's the, and here's where the machine learning part comes in. This is why people haven't been doing machine learning on optical flow, because there hasn't been any ground truth sequences. So why is that? Well, yeah. Yeah, so early on people tried that, and they tended to produce very crappy image sequences. You know, you got a computer vision graduate student who doesn't really know much about graphics, and they make a little synthetic thing, and it doesn't really reflect the real world. So generating synthetic data has been really hard. Hollywood will do it for you. And years ago, I went to people in Hollywood and I said, please, please, please give me your 3D, all the information that you use to generate your movies, and then I can generate ground truths. And they all said, well, the people that do the graphics, they don't actually have the copyright for it, and the studios that own the copyright have no interest in giving it to you. And so that whole thing died. The other thing, so unlike something like the Kinect sensor, which is a camera with images and depth information, there's no camera in the world that measures the motion of pixels directly. Like there's no direct sensor that computes like how all the pixels are moving. So there's no way to just go out and capture lots of data like people are beginning to do with Connect. So you really have to rely on either some kind of really laborious manual laboring or complicated instrumentation of the world, which then makes the images very unnatural, or you have to get some graphics data. And so we got some graphics data. And this was an idea of Dan Butler's. He's a PhD student at the University of Washington, and it's joint work with Jonas Wolf here at MPI and Garrett Stanley from Georgia Tech. And the idea is that there are actually there are some people out there in the world making movies and making them freely available. So the Durian open source movie project uses Blender and a community of animators all around the world to make animated movies. And it was a really nice movie called Sintel. If you haven't seen it, I highly recommend watching it. It's a very nice movie. And so they made this movie, and then they put all the data online. So we finally have something that we can study. Now, I'll come back to some important issues when you think about using a synthetic movie, but I want to give you an idea of what ground truth optical flow really looks like in a complex scene. So here are scenes from Sintel, and here's this color coding of how all the pixels in the image are moving. And this is not the original Sintel, it's slightly modified by us, but it gives you a sense of the complexity and the richness of what's going on. And it's a data set with over 1,600 frames of ground truth data. These are widescreen, fairly high resolution. We have it divided into training and testing sequences, and with large velocities of over 100 pixels per frame. And it's online, and if people are interested in it, you can go to, I'll give you the address in a second. So the problem is, what can animated movies teach us about optical flow in the real world? And as soon as you start to do anything in computer vision that uses graphics data, everyone gets really, really nervous and asks, is it realistic enough? Does it really, if I learn something from a graphics movie and then I take it and apply it to real images, will I have learned the wrong thing? And so what's really important is, are the statistics of the world in Sintel realistic enough for us to learn something of value? And so what we did, this is really hard to do, but what we did is we constructed a set of what we called lookalikes. So here's a Sintel scene of flying through some mountain, and here's a scene from Batman, Batman Returns or something, which looks kind of visually a lot like it. So we searched the internet for scenes that had similar kind of semantic content to Sintel, and you probably can't see this, but here's a campfire scene in Sintel, and here's one from Dances with Wolves. And here's a market chase scene in Sintel, and here's one from a James Bond movie. And here's running through a bamboo forest, and here's some like crouching tiger, hidden dragon scene or something like that. So it turns out there's a lot of scenes in Sintel that are very much like scenes you've seen in real movies. We actually went to there's a whole Sintel group of animators, and we went to the news group there, like the forum where they communicate, and asked for people's ideas of what scenes in other movies were inspirational for scenes in Sintel, so we could, because often they were so offended. They said nothing in Sintel is completely novel. It's not like anything else in the world. It's just, they were very offended that we even thought there might be similar things. But you can see that, maybe they were inspired by some of these things. So one thing we had trouble finding was fight scenes in the snow, but it turns out there's a whole group of people in the world who all they like to do is take a home video camera and make fight scenes in the snow. So we were able, and it turns out, to find a lot of people fighting with swords in the snow, a lot of bamboo forests. These are some of the lookalike sequences on high speed. But the question is, so they don't look exactly like Sintel, but are they similar enough? And so then we started asking about the natural statistics in these scenes. We looked at the image statistics. And so, for example, one thing people look at is the marginal image derivative statistics. So this is the log histogram of horizontal and vertical derivatives of the image intensity function in Sintel, which is the red line, and in the lookalikes, which is the blue line. And they line up pretty well. What does that tell you? Not a whole lot, but these are characteristics of what people who study image statistics see, that the derivatives are peaked at 0. Mostly things are kind of flat. And then there's some large outliers, and so you get these heavy tails. So you can ignore the green line. It's for now, forever, unless you get interested in this. Now, so that's saying that the images at least have the right kind of first-order statistics. Okay. The question that's maybe more interesting is, does the motion have the same kind of structure? And this is a little bit harder, since there's no ground truth motion for those sequences. So we did something a little bit fishy, which is that we computed optical flow using an algorithm on Sintel, and we computed optical flow using an algorithm on the lookalikes. You have to assume those algorithms behave sort of reasonably, and then we compared the statistics of those. And what we found is that on Sintel and the lookalikes, this is a little bit hard to see, but there's a red line and a blue line here that kind of lie on top of each other. These are the log histogram of the horizontal motions and the vertical motions, and they're sort of similar. They're quite different from this dotted line, which is the ground truth histogram, log histogram of horizontal and vertical motions. That's because the algorithm isn't able to capture the large motions present in Sintel. But at least it gives us some confidence that there's something similar about the motions in the two scenes. And finally, if we look at the statistics of the spatial derivatives, so here's the spatial derivative of the horizontal motion in the y direction. So it's a partial derivative of horizontal flow in the y direction for the lookalikes blue and Sintel red. And you can see these two things line up fairly well. That's good. But you also notice that they don't look Gaussian at all. They're very peaked at 0 and highly kurtotic. So that suggests that our spatial smoothness assumption was probably wrong. So now that we have a database of images with ground truth, image sequences with ground truth, let's come back and look at some of our assumptions. Start with this brightness constancy assumption. So we have all these images, we've got these flow fields. We now know which pixels from frame 1 look like correspond to pixels in frame 2, and we can just look at the statistics of the brightness constancy difference. So image 1 at pixel ij, image 2 at ij offset by the true flow, and we find that they're heavily peaked at 0, and again highly kurtotic with heavy tails. So this doesn't look very Gaussian. So these are just the marginal statistics, but the truth is this came out of an 08 paper which didn't use Sintel. It used a different training set that was much smaller. So I couldn't find the figure this morning for Sintel. So my guess is Sintel's more symmetric, and that's just not enough training data. And then the spatial term. So remember, we're assuming that a pixel here should look like its neighbors, but in fact, what could easily happen here is something like this, where we're looking at a pixel, and it belongs to some surface, and then the neighboring pixel here, it belongs to a different surface moving a different way. So in some sense, you can think of this as a spatial outlier, and that you want to be able to detect that this belongs to this surface and not this surface. So again, this is out of an old paper. I don't have the Sintel picture in here, but these are the horizontal and vertical derivatives computed a different way, but you get the same idea of heavily peaked at 0 and heavy tails. And these heavy tails mean that the sharp peak means that optical flow is usually smooth. So that assumption is pretty good. The world is pretty smooth. But you have these large discontinuities where there's one surface moving behind another surface, and they're with different motions. And so you really do have to model these things. So this goes back now to my PhD thesis. I introduced this robust penalty function, which has roughly this kind of shape. This is the negative log of this thing, basically. And it's because remember, we're working with this energy function instead of the probabilistic formulation. So this rho function here is just one of the ones I used, and it has the nice property that as the errors grow large, so this would be, for example, brightness error or spatial derivative, the penalty you pay saturates. So this means you can't be too influenced by some crazy measurement. And if you just take the quadratic out of Horn and Schunck and you replace it with this rho function and choose the right robust rho function, you can get a very nice result. And there's a bunch of things we could choose. Here's the quadratic of Horn and Schunck. Here's something that I used in my thesis, which I just guessed that maybe this would be good. I didn't. And then here's something called the Charbonnier, which looks like an L1 error, which is nicely robust, but it's continuous at 0, so it's differentiable, which is nice. Now, if you plug in one of those robust functions and just take the exact same, everything is exactly the same, except I've replaced the quadratic with something robust, you'll end up getting much sharper discontinuities here, and so you don't get the spatial blurring that you would get with the quadratic. So that makes sense. That's a step in the right direction. But what robust function to choose, right? That is where we can begin to leverage the data set that we have now. Now, there's several issues here. The optimization just became a lot harder. We can't just differentiate this and end up with a system of linear equations and solve anymore. So there's a bunch of things we can do. We can do gradient descent. We can start with a convex solution and then gradually make it non-convex by starting with a quadratic and gradually introducing some more robust shape to the penalty function. We can use iteratively reweighted least squares so that we solve a series of linear equations, and then there's a bunch of ways to go. But you get something that matches the world a little bit better, but it's just a little bit harder to deal with. So that is where we get into a bunch of modern techniques for computing optical flow. And how am I doing? I'm okay. And there's a bunch of things that matter. So we now have an objective function. We know that coarse define helps for dealing with large motions. I'm going to tell you something about median filtering in just a minute. Graduated non-convexity is this: how do I track, how do I deal with a non-convex energy function? There's a bunch of other things. And in fact, in this paper that just appeared, it was originally a CVPR paper, but just appeared today, we look at a whole bunch of different things. And I'm not going to go through them all. In yellow are the ones that I'll just touch on briefly. And, well, I already touched on coarse define. I'll tell you only about median filtering and then the penalty function that we're going to use. But if you want to learn more about this, there's a detailed evaluation. Now, I mentioned that evaluation is important, and we're going to, you have to decide what's a good optical flow field. And so I'm going to use EPE, which stands for average endpoint error. And so if the ground truth motion is this yellow thing and my estimate is this, EPE is the Euclidean distance between these points. You could also compute angular error, but they basically give the same kind of results. So using a data set with ground truth, we can look at different penalty functions, the quadratic, this Lorentzian one, the Charbonnier one, and ask what is the average endpoint error like using these different terms. And we see the Charbonnier is a little bit better. We can test the significance. Classic C is using Charbonnier, and we can compare that with Horn and Schunck, the quadratic, or classic L, the Lorentzian, and the difference is statistically significant. So this classic C thing seems to be good. In fact, it turns out that a little bit of even a little bit more non-convexity is better. You can write this Charbonnier in this way with an A parameter here, and the classic Charbonnier, this is 0.5, meaning this is like an L1, but values slightly smaller turn out to be better, and we found that just a little bit more non-convexity really helped a lot. So then there's one other key thing that is a little trick that people were doing and not really telling anybody about. So in their paper, hang on a second, I'll show you this. When you're computing the optical flow, it would sometimes be kind of noisy, and people thought, it's kind of noisy. Maybe if I just run a median filter over the optical flow field, that'll clean it up. And it turns out that works great. It really cleans it up. If you turn on a median filter, the average endpoint error goes way down, much better than if you don't do this median filtering hack. It's just a little hack. Here's it with it on, here's it with it off. These are normalized, so actually there's some little outliers here that are making this look very, are sort of squashing the intensity function here, so you don't really see the structure. But the endpoint error in this image is significantly lower than in this one. And so the thing, we looked at this and then realized that, you know, we're trying to optimize this energy function, and if we plug in this median filtering step, this hack, we end up with a higher energy but a lower endpoint error. So what that means is, well, it means several things. It might mean that it means our objective function is wrong, or that we're not optimizing, that the solution we're finding is good, but it's not actually optimizing our energy function, which means we're optimizing implicitly some other energy function. And so we started to think, well, what is that? And it turns out we can rewrite this, and this turns out to be an important thing. Before we looked at spatial neighborhoods that were very small. We just looked at the nearest neighbors of a pixel. This isn't very powerful. It just tells you a little bit about, you look at the first derivatives. It's much more powerful to look at a large neighborhood, but the question is how to do that. And the median filter gives us an idea. What's actually happening in the median filter is we're looking at a whole region and its optical flow, and we're trying to compute a median value. And you can imagine then setting the center pixel to be this median value. Another way to write that is, as we've written it before, here's our data term as before, our spatial term as before, and a new constraint that says that this neighboring pixel should look like all of these, so not just its 4 neighbors, but all the neighbors in, say, a 5x5 region, with a L1 penalty term. So this is basically computing a median, and we can add this into this equation. That's roughly what people were doing. Now, it turns out to be hard to optimize this thing. So what you can do is you can split it into 2 pieces and reformulate it so that we introduce an auxiliary optical flow field here that I'll put a little hat on. And this little hat, we're computing a median, basically, over the optical flow. And then we're connecting, this is our optical flow equation we had before, and we're connecting them through this, and it's like a spring penalty in some sense, a quadratic penalty to make those 2 things the same. The advantage of doing this is when we differentiate this with respect to the UVs, this term drops away, and when we differentiate with respect to these things, this term drops away, and then we have an alternating optimization between those 2 things. So this allows us to compute a median filter and then couple it to the original optical flow equation, and this median alternating thing I just described, or this one here, gets the same results as the median filter. But it now gives us an explicit objective function that we can understand. We've introduced this non-local term that allows us to have integrate information in a large spatial neighborhood. And that's a great thing, except when it's not a great thing. So what happens when you do a median filter, if you've got some very thin, small structure, like this gun here, and you look in the neighborhood around the tip of this gun, most of the pixels correspond to the motion of the background, not to the motion of the foreground. And so the median filter actually blurs away the tip of the gun. So it gets rid of small structures. But now that we've introduced this spatial neighborhood term, and it's not just a median filter, we can begin to look into what's going on there. And so we're going to introduce now a weighted non-local term, which is going to have a new assumption that motion boundaries are likely to coincide with image boundaries in the image. So let me explain that. So here we have this median filter that we're doing. We want the center optical flow value to look like all of its neighbors, except now we're going to actually compute a weight to each of these neighbors, and that weight is going to vary. So, and where are we going to get that weight from? So here's the weighted median we're going to compute. We're going to get that by looking at the image intensity and some other properties here. So the further away I am from the center pixel, the less I want it to contribute. And, or said the other way, the closer I am, the more I want it to contribute. The more similar the image intensity values or color values are, the more I want it to contribute. And there's another term here for how similar the optical flow vectors are that I won't go into. And so if we do that, we get the following masks or weights associated with a particular pixel. So take the center pixel here on this gun of this little toy soldier, and the brightness here indicates the weight in this weighted median filter. And so things that are on the gun have the same color, and therefore they end up having a higher weight. On a, let's see, B here is on the boundary between this fence thing and the background. And so the center pixel prefers motions or pixels on the left side here. This pixel right here in this little V, it likes pixels up here. So this is a way of incorporating image information into the optical flow equation, and it works like dynamite. So let me, here's the ground truth optical flow, here's the estimated optical flow, ground truth and estimated, and they're starting to look quite similar. So this we call classic plus NL, and NL stands for non-local, and it's a significant improvement. So here's just with a regular median filter, here's with a weighted median filter, built into the objective function in a nice way, and you can see that it really matches the image pretty nicely. And this is true at motion boundaries as well. So I promised you some code. So this is all on Deching Sun's webpage. If you search for Deching Sun, you'll find his software. It's widely used, and he's got all these things implemented in lots of different variations. So it's easy to build on it. It's all in MATLAB. But in the 10 minutes I have remaining, I would like to point out a few problems. So here's classic plus NL applied to this sequence, and you see while it does a reasonable job of maintaining motion boundaries and getting a nice smooth flow that looks like this ground truth, it still screws up in some places where there's really fine structures and occlusion relationships. It misses these little very fine, bits of the leaf here, and so it's not perfect. And what's really going on here is we formulated this classical model derived from Horn and Schunk. And we've found that motion boundaries are critical for accuracy, but this model doesn't really explicitly say anything about boundaries. It's not in the model. What we're doing is asking this little robust penalty function to do two things for us at once. To implement smoothness, that is, to constrain neighboring pixels to have similar flows, and at the same time to allow them to be different if they need to be different. It's an awful lot to ask of one little function. And so what's really going on here is that there's some kind of segmentation that needs to happen. So there's really, there's sort of two problems that exist in the computer vision literature. One is segmentation, one is motion estimation, and they tend to be treated separately. So here's an image of a scene, a single frame. Here's a segmentation produced by a particular segmentation algorithm. It's fairly representative. And what you can see is that from a single image, the segmentation about the 3D world is often ambiguous. So here, for example, this can gets merged with the background segment. And things get over-segmented too. This can get segmented into all kinds of things that makes it look like multiple objects, even though it's one object. From the optical flow information, if we had the ground truth optical flow, it would give us a very nice, precise segmentation information about where the objects are. But of course, we don't have the precise optical flow information. So the question is, can we combine this problem of estimating flow with this problem of segmentation, so that solving them together, we can use cues about the image, cues about the motion, and get a better segmentation of the scene and a better optical flow estimate. So this idea has a long history and goes it back at least to the work of Wang and Adelson in 1993 on a layered model of optical flow. And so this is an important one to think about because it's a very nice simple model. It introduces a bunch of new assumptions, but the key one is that the image can be decomposed into a series of overlapping layers. Each layer has maybe a fairly simple motion associated with it. In this case, the background is moving in one direction. The foreground, there's an alpha map, which is the segmentation, and the foreground's moving in another way. And the generative model of an image is as I take my background pattern, I take my alpha, multiply it by my alpha mat, and I take my foreground pattern, multiply by my alpha mat, I add them together, I get an image, and then I can warp these and generate a sequence of images. It's a very simple generative model of an image sequence, and it explicitly puts in this segmentation model. So it's a very nice place where you can incorporate information about image segmentation. So I'm not going to go into the details, but with the Ching Sun and Eric Suddereth and some others, we have a series of papers on doing this, where we revived this idea of a layered segmentation, and now we take a sequence like this and simultaneously segment it into layers. And you see here these very fine structures are captured by this segmentation because it's using image information to do the segmentation. And it allows us to model explicitly what's happening at an occlusion boundary. Rather than trying to wrap it all up into this little robust function, there's an explicit generative model of what's going on at the occlusion boundary, which allows you to do a much better job of estimating the flow. So I think this is an interesting direction to go. Oh, and we can estimate. Here are the black, here are the ground truth occluded regions, and here are estimated occluded regions. So apart from tuning some parameters and maybe learning some marginal statistics, there really hasn't been much learning in this field. And so why, okay, now that you've seen this presentation of the sort of classical formulation, do you have some ideas of why machine learning hasn't been used more? Or well, number one, there wasn't training data before, but now that we have some training data, are there places where you think you could start to think about machine learning? Yeah. Yeah, unfortunately, the layered model is kind of nice and simple, but it turns out most scenes don't actually come in a nice series of layers. If you think about walking in a forest, you have a ground plane, and you've got all these things sticking up out of the ground plane, and sometimes the ground is in front of the trees, and sometimes it's behind the trees. So it's not. It turns out not to be. It may not be the best model, but indeed, to train a layered model, we don't have any ground truth about what those layers might be. So getting ground truth is probably the biggest hurdle. There's some other problems. So lots of this optimization I talked about makes things a little bit specific to the problem. So this having to deal with large motions and the fact that people have done it in a course-defined way kind of restricts how you think about the problem. And if you don't do it in this course-defined way, you have a very, very difficult optimization problem where you have any patch of the image could go to any other location in the image, and it's a horrendous search problem. And the other thing is this image sequences are just not as nice as images. And so, for example, if I think here's a little patch in an image in one frame, and if I'm thinking about learning a convolutional model or something to represent the images and denoise them, I can imagine looking at image patches in lots of frames. But the question is, what happens when I introduce a temporal sequence? If I look at the next frame, the thing that was in that patch isn't there anymore. So I've got this problem if I want to just do something naive, which is just say I'm going to take a sequence of frames and take regions and look in these regions, and I'm going to try and learn something about how things move. I've got the ground truth motion, I've got the images, I should be able to learn from a little spatiotemporal volume what the flow is. Except I can't do that here because the things move too fast. So there's some scale thing that makes naive application of machine learning algorithms really problematic here. Just to let you know, like, okay, this classical formulation, we talked about a bunch of the assumptions. There's a whole bunch of stuff that still breaks it. Complex stochastic things with appearance change, raindrops and puddles. It's not clear what the optical flow is. It's not clear what the optical flow should be. Fire and waves and so on. Again, it's not clear even what the definition of the problem is. Like, what's the right answer for the optical flow of a bunch of waves or something that's exploding? What's the right motion for a car with a pole reflected in it? Is it the motion of the car? Is it the motion of the pole? Is it some combination? Should I actually be thinking now, I told you not to think about physics, maybe I should think about physics again and think about reflections and maybe actually be modeling the material properties of the car and the image around it and how it's reflected by the car. I don't really know. What's the right optical flow for things like plants blowing in the wind and flags? Does anybody really want a detailed pixel motion of all the leaves on this plant? I mean, maybe someone just wants some kind of coarse textural information to say, oh, it's clearly a plant blowing in the wind. I don't know, it's sort of problem specific. I don't really know what the right answer is. And then one fundamental problem is small things moving fast. So this is even a problem for the classical formulations. So this example I showed you, the motions are so large that even at the coarse level of a pyramid, because this structure is so small, by the time you subsample and subsample and subsample and subsample it so much that the motion is less than a pixel, you can't see it anymore. It's disappeared. So the motion of small things moving quickly is really a fundamental problem. So, and another thing that's missing is I only talked about 2 frames here. And obviously the world persists. There's temporal continuity. The question is what persists in time? And the optical flow is something that in a sense might not persist in time. It's the physical structure of the world that persists. And so again, one might want to start thinking about the physics of the world and surfaces and their properties. So I promised to finish now, and I will finish now. Sorry for going so quickly. The things I wanted to get across is that some of the early ideas, going all the way back to the 80s, were not so bad. The idea of Horn and Schunk, and then the layers idea of Adelson, Wang and Adelson, are pretty good. The assumptions were wrong. The assumptions can be improved. We can use this relatively realistic synthetic training data to improve them and to train the models. And that the problem is not yet fully solved. Maybe it's not even fully defined yet. And that moving forward might mean thinking about the problem in a very different way, more of a physical representation. But I also want to get across the idea that optical flow is actually pretty useful. So you might not be interested in using machine learning algorithms to improve optical flow estimation, but you might walk away from this with some optical flow code and say, maybe I can use that in my problem. So for example, Sylvia Zuffi has a paper that's going to appear at ICCV where she uses optical flow to help figure out human pose estimation in a video sequence. And it turns out if you just look at little movies of people moving around, just look at the optical flow, you can actually see a lot about what it is they're doing. And so here's some nice examples of estimating the pose. And you see the optical flow underneath the pose of this puppet. If you want to know more, you should ask Sylvia about it. That's just one example among many where optical flow today is good enough to be useful. And then this Syntel training set, if you want to play with it, you can download it from our website. Here's some more examples of the training data in there, just to give you an idea of the complexity. All right, I'm done. I don't know, do we have any time for?
I think we have a bit of time. Thank you very much. Perfect timing. So questions, please. Yes, in the back.
Yeah. Yeah. Yeah, go ahead, shout.
Okay. So,
I can repeat it.
curious, in working through your assumptions, did you ever look at the compositional nature and function of the retina?
Of the what?
Retina.
Of the retina. So good question. So the question is, should we think about the retina? So what is, the retina's got some different properties. For example, it's got a high resolution fovea and a low resolution periphery. Some people have looked at camera models that have similar properties. So you might imagine that in the periphery you get very low spatial frequency information. You can kind of get the gist of the overall motions. So far, you know, that hasn't been terribly useful because most people don't want a camera that's like the eye. They want to, you know, they want to compress a movie sequence like this or understand a movie sequence like this. So far, biologically motivated models derived from the retina or from models of processing in the brain have not been terribly successful. Maybe that's just because we don't know how the brain works.
Okay, so there's a second question here.
So the question was, there's also in a lot of these movie sequences, objects are either coming closer to the camera or going away from the camera, so their size is actually changing. Any information on that? What do you think of that?
So indeed, so going back to Gibson's whole motivation for this is, so if something is coming towards me, it creates a looming pattern, and you can write down very simply that this is just an expansion of the optical flow field, and you can get it out very quickly that something is coming towards you. So you could imagine implementing a detector that very accurately predicts when I'm going to come into contact with an object, how I'm approaching an object. It tells you about your head, not just whether something's looming or moving away from you, but your own heading in the world. So these are all applications of the optical flow field that people have looked at. Yeah.
Yes, please.
Are there already approaches to estimate the three-dimensional optical flow from stereo?
Yeah, it's a good question. So there, in addition to this 2D optical flow I talked about, there's something called scene flow, which is a three-dimensional vectors describing the 3D motion in the world, the thing that we started out with. To get that from single images is actually quite hard, and unless the scene is, you can assume the scene is rigid. If you can assume the scene is rigid, you can do a whole lot of things. But in general, the scene isn't fully rigid. There's lots of stuff moving around in it. And then people have been using stereo, and there's a few formulations that do stereo and motion together. We're extending this Syntel data set to actually allow people to do something like that, where we will have the stereo pairs and the optical flow, and then people can do the both together. We're still trying to come up with exactly how to generate the evaluation data for this scene flow problem, but hopefully we'll get that online later this fall.
Further questions?
Yeah.
Yes.
If I'm not being so wrong,
Mm-hmm.
in the field we had another problem of inferring objects from single images.
Mm-hmm.
Couldn't you use that to infer objects and then look at the objects during time to limit that crazy optimization problem that you had to capture those fast motions of the picture?
So you're suggesting that if I knew what the objects were in the scene, then I have a simpler problem of pose estimation of those objects over time. Absolutely. But that's a hard problem. So people have often thought, well, if I got the optical flow, then I would know where the boundaries of things were, and then I would know where the objects were. And you're saying, well, if I knew where the objects were, then the optical flow problem would be easy. Indeed, there's often these chicken and egg problems. And so the interesting thing is, can I maybe formulate those two things together? That's what the layered model tries to do for a very simple case of doing segmentation and motion estimation together. But you're suggesting maybe I should, for example, maybe in a simplified world this could work. So I'm driving down the road, I've got a camera, and I know what I'm going to see are cars, bikes, and pedestrians. So I might have fairly simple models for those. And the optical flow problem is now one of estimating the motion of these, detecting the objects and estimating their motion. In an arbitrary scene, it would be pretty hard, but in a constrained scenario, maybe you could formulate them together.
More questions?
Yes.
Yeah.
I'm guessing a lot of the problems occur at the edges.
Of the image,
Of the objects.
the boundaries of the objects, yes, yes.
So would there be any value in kind of treating them separately to the objects?
That's a.
Using separate algorithms for
So this is a very good question. So the question is really like, the assumption is absolutely right. Where do optical flow algorithms really break still? Well, I told you some places, but one is at the boundaries of objects. And you want optical flow so that you can find the boundaries of the objects, but the boundaries are the places where optical flow doesn't really work very well. And so should you do something special for the boundaries? And indeed, that's something that I've worked on several times, formulating specific models for detecting and modeling what's going on right at the boundary. You can do that. I think these layered models are a good way to go in some sense, because they tell you the motion of the foreground and the background, and it allow you to make inferences about the stuff that you can't see. So if I have something moving in front of something else, between two frames, some stuff disappears and some stuff appears. And if I can track the layers over time, then I can make good inferences about what's really happening at the boundary. So I think to do the boundaries well, estimating motion over multiple frames, where I particularly try and estimate the structure, where those boundaries are over multiple frames, and make sure they're consistent across time, I think you could do really well.
More questions? So maybe before we thank Michael, maybe it's also a chance for a little advertising. So you met, or you saw Michael, you saw Stefan, you saw me, you saw a number of other people here from the Institute. We're only getting started. We're doing a new building. We will be hiring a fourth director, so we will have 4 departments in Tübingen, plus we have 4 departments in Stuttgart looking at hardware issues. So I think we're really excited about the future, and this will be an interesting place. So if you go home with this idea, tell others about it, think about your own professional future, etc. Keep us in mind. We'll be happy to see some of you again later on.
This is one more video. One more video.
Go ahead.
So you're off?
We are also having a question in the observation room.
Okay. But while the question is coming in, just to get at the neural question about the retina, this is a video sequence that was shown to an anesthetized cat. And typically when people study motion in the brain, they use very simple things like sinusoids, moving, drifting sine wave gratings and things like that. And our hypothesis is that that natural scene statistics are actually really important to the brain, and that if we study motion processing in much more natural scenes, maybe we'll learn something different. And what you're seeing are LGN neurons in the cat, on and off cells, red and blue, responding to different kinds of things, both image structure as well as motion in the scene. And with Garrett Stanley and Jose Manuel Alonso, we've been looking at using natural scenes like the ones I showed you from Sintel to get maybe a richer model of what it is the brain might be doing and how what the neural code is for motion. And so we have a paper on that. That's a beginning, little beginning.
So question from the observation lounge.
This is related to the scene flow estimation. So when I'm trying to estimate the three-dimensional velocity of objects or moving scene, do you think it is important to use dense optical flow? Like if I use a sparse optical flow using image descriptors, do you think it should serve the purpose?
It's a very good question. So this comes down to something I touched on at the end, is the application really matters. And if all you want to do, for example, is figure out how the 3D camera motion, then you should probably track some sparse feature points and do a ransack algorithm or something and try and figure out the camera motion. If you want to do image coding, maybe you need to know something more dense. If you want to detect motion boundaries, maybe you need something more dense. I think it really depends on your application. And there's lots of applications, I think, where some sort of sparse representation of the scene may be sufficient.
One more question on the observation.
Okay.
Subjective versus objective optic flows. You made the point at the beginning that it's important to define it subjectively rather than objectively in terms of real motion. But in your Sintel, objective flow rather than subjective flow.
Yeah,
so how do you
indeed.
go between those two?
Indeed. Right, I should have made this clearer. What I really want out of the world, out of an image sequence, is the motion field. I would really desperately, that's what I would like to have. If I'm doing image coding for motion JPEG or something, I don't care about that. I only care about the apparent motion. But if I want to build an intelligent system that moves around in the world like a living organism does and uses the motion in the environment, then I think it really wants to get at the motion field. My point in the beginning was that you can't always do that, but it's what we would like. And so when we evaluate algorithms with respect to Sintel, we evaluate them in sort of the most difficult way, which is that how well did the optical flow algorithm do at getting back the 3D structure, or the projected 3D structure of the moving world. And to do that, you might argue, well, maybe you should be actually formulating it as a motion field problem, formulating it in the 3D world. And I was hinting at that towards the end of the talk.